Welcome back. In today's class, we will look at some important concepts which is necessary for augmented reality. The concepts we have been looking at so far in the class is for virtual reality as well as the augmented reality. The concepts can be used both in virtual reality as well as the augmented reality. But there are some concepts which is necessary specifically for the augmented reality. For example, if you look at the augmented reality, we need to augment the existing environment with a virtual objects. We need to know what is the already available room in an environment, physical environment, and over this physical environment we should be able to overlay the virtual objects, right. So, we should be able to measure the physical environment in real time. Okay. So, there are specific algorithms which is required for augmented reality called SLAM, SLAM, SLAM for simultaneous localization and mapping. Simultaneous localization and mapping. So, there are two things happening, localization and mapping, and that is simultaneously happening. Localization is to estimate the pose of the camera in a augmented reality, to estimate the pose of the user where exactly he is, and mapping is to have a 3D modeling of the environment, so that we can place the virtual object onto the real environment, so that we can overlay the 3D objects, virtual objects into the physical environment in the camera images. Okay. There are many SLAM techniques which have been proposed in the last 20 years. There are essentially these are all sensor fusion algorithms, sensor fusion techniques. This techniques, SLAM techniques, uses mostly IMUs and multiple cameras, multiple camera images, and depth camera, and so on. So, the SLAM technique takes input from all these things and then estimate the pose as well as the mapping of the 3D environment. In this class, in virtual reality, what may be required is a particular classes of a particular class of SLAM technique called visual SLAM. It is also called the VSLAM. So, in VSLAM we focus only the algorithms which takes input from the camera. So, this technique takes input from camera alone, and this VSLAM can have multiple camera inputs. There are even another class of VSLAM which is called the monocular SLAM, which takes input from only one camera, takes input from one camera alone. So, this will be the very simple VSLAM technique which we will focus in this, and also the SLAM techniques which is discussed in the many of the reading materials over there uses many mathematical notations which scares away the students. So, I am going to reduce the uses of the mathematical notations and then make it as an intuitive introduction to the SLAM technique in this next few minutes. In this example, I am going to introduce very simple motor vehicle moving in the road. Let us say this is the road we are talking about, and this motor, we need to look at what is its position. Let us say this position, we need to measure it, and let us say here is the sensor which measures the position. So, when it measures the measurement distance, it measures the distance, right. But what happens is this sensor is noisy. The output of the measurement and of the sensor itself is noisy. So, we are not very confident about what the sensor is. Most of the sensors are like this, it is uncertain, the measurement is a little bit of uncertain. So, in the case of the uncertain measurements, how are we going to make better measurement of our objects in the virtual reality environment is a question. So, we are talking about how do we improve the noisy measurement process. What Kalman filter does it uses some prediction algorithms and then uses this prediction algorithms to update the measured distance, for example here, and then the measured distance is used to predict. There are the two stages in the Kalman filter. So, in a normal process, what we would do is we will use only the measured distance without worrying about the prediction. Measured distance and using it directly is a little risky because the data is noisy. So, to avoid this, Kalman filter does it is that it uses some special prediction algorithms and uses this prediction algorithms to update the measured distance. Okay. So, the measurement distance is not directly used, but it is updated based on the prediction as well as from the measurement data. Once we update the measured data, then we use it to predict again. Okay, these are the two stages of Kalman filter, right. So, in this example, suppose we have the vehicle moved little ahead, then again we have this sensor, and the measurement it gives you, since it is noisy, it is modeled as a simple normal distribution. Instead of having only one value as in the Kalman filter, as in the complementary filter, in the Kalman filter the measured data is not one single value, but one single value, that is the mean of the data, and also a normal distribution. As you know, the normal distribution has the mean as well as the variance. So, the measurement comes with the mean and the variance. Okay. So, in this case, this example, let us say we have this mean and variance. Now, let us say we have an algorithm to predict the position depending upon the previous data. Let us say this is the predicted data. Let me take another one, another color, and let us say this is predicted distance. The predicted distance also has a mean and a variance. Let us say this is a 1 and this is 1, and the measured one is this one. Now, combining these two things, we need to do the updating. So, we have the measurement distribution, we have the prediction distribution. Combining those two things, we can update it, which can be yet another distribution. Let me make this as a probably green, yellow, I do not know whether that looks like. Okay, let me put it as a black. So, it can be another distribution. Let us say this is the updated one, or updated or fused. Let us say fused. This can be comma 0. So, this is one of the very nice properties when two Gaussian distributions, when two Gaussian distributions are multiplied, the resulting Gaussian distribution is also resulting we can say resulting distribution is also a Gaussian distribution. This is a very nice property. It is guaranteed to have the resulting Gaussian distribution. So, the predicted distance itself is a distribution. The measured distance is also a distribution, Gaussian distribution. When these two things are together multiplied, say let us say fused, the resulting itself is again a Gaussian distributions. So, we can write equations for what is the mu of the fused data, what is the variance of the fused data is a function of mu naught and mu 1 and sigma 1 and sigma naught, right. Similarly, this also sigma 1 and sigma naught. Okay. We can write an equation and for the what is the phi mused or what is the sigma mused. Okay. So, essentially if you look at if you take a Gaussian distribution, x is a measurement distance we are talking about, mu is the mean and sigma is the variance, then this is a standard equation for the Gaussian distribution, Gaussian bell shaped curve. It is e power minus as x minus mu whole squared divided by 2 into sigma square, right. This is the standard bell shaped Gaussian distribution. If you look at mu 1 mu fused, then it is going to be mu naught plus sigma naught squared into mu 1 minus mu naught divided by mu naught squared plus mu 1 squared. Similarly, we can write sigma fused is going to be sigma naught squared minus sigma naught squared divided by sigma naught squared plus sigma 1 square. This is the equation for the fused distribution. in this, if you observe, if you consider the whole thing as some constant k, then and this also is going to be k. Therefore, we can write again the same equation, fused is going to be mu naught plus k times mu 1 minus mu naught, sigma fused is equal to sigma naught squared minus is k times sigma naught squared. Yeah. So, here there is one term missed, it is actually is going to be k times this is going to be sigma naught squared again. Okay. So, this is going to be sigma naught squared. Okay. So, this k we can consider this as the Kalman gain. So, this again is a Kalman gain. You can compare this with a complementary filter which makes it a little more easier. In the complementary filter we use a complementary gain, filter gain, right. Similarly, we have this Kalman gain. Only thing is here we need to add the variance also into picture, because the Kalman filter is based on the distribution, probability distribution, in order to handle the uncertainty. This is for the 1D whatever we have seen it, right. If there are many parameters as are involved, more than one measured variable, let's say what not only x but also velocity, then and the calculation becomes much more difficult. So, usually the Kalman filter discussion or the derivatives in the textbooks and other materials you will see is in the now matrix notation. So, I am going to introduce the Kalman filter in the matrix notation, and again without much of the mathematical notation, and so that you are not you are familiar with the Kalman filter when you come across in your textbooks. So, essentially we have as we have seen in the earlier slides, there are two stages of the Kalman filter. One is the prediction stage and then the update stage, right. We will stop here. Thank you.